Let's wrap up the chemistry of aldehydes and ketones by talking about mostly hydrogen and carbon nucleophiles. We've already learned these reactions for the most part. Those include Grignard reagents, lithium aluminum hydride, sodium borohydride. We'll introduce some new reactions, formation of cyanohydrins, and also a reaction called the Wittig reaction. And then we'll include one reaction that kind of doesn't have a good place to go, the Baeyer-Villiger reaction, which is technically not the addition of a hydrogen or carbon nucleophile. And that'll wrap up reactions of aldehydes and ketones. So let's start by talking about some reactions that we're already familiar with, right? We know that if you have a ketone, and we react that with lithium aluminum hydride or sodium borohydride, we get an alcohol, and that's because we have a nucleophilic source of hydrogen that adds to the carbon of the carbon-oxygen double bond. So just to refresh our memory, if we had, let's say, acetone, we reacted that with lithium aluminum hydride. Remember, an aluminum hydride, the hydrogen has a partial negative charge. It's more electronegative than the aluminum. So the hydrogen attacks this carbon under basic conditions. Is a good enough nucleophile it can just attack right away without transferring a proton first. So that results in a new lone pair of electrons on oxygen. We get a negative charge here. We add water, which is a source of protons, in the second step to protonate that oxygen to get our secondary alcohol. Okay, so that's metal hydrides. Also remember the Grignard reaction is basically analogous to reduction, except instead of a nucleophilic source of hydrogen, we have a nucleophilic source of carbon. If you take a ketone and add a Grignard, you get a tertiary alcohol. If you take an aldehyde and add a Grignard, you get a secondary alcohol, as we all remember. And again, just to refresh your memory, right, a Grignard reagent is a nucleophilic source of carbon, right, because magnesium is less electronegative than carbon. Carbon's our nucleophile. This bond is our nucleophile that attacks the carbon. We break the carbon-oxygen double bond, so the result here is an O- and a new bond, new carbon-carbon bond, and then we add water as a source of protons in the workup to protonate that oxygen. So the lone pair of electrons grabs that hydrogen to get our tertiary alcohol. So we're all familiar with these reactions, right? But if we understand these mechanisms, we can understand some of the reactions that we're going to talk about in a second here. Okay, so the first new reaction we're going to talk about is formation of cyanohydrins. Remember, the first thing you always want to ask yourself is, are the conditions acidic or basic? In this case, it's a little ambiguous, right, because cyanide is a base, HCl is an acid, but HCl is a stronger acid. It's a very strong acid, whereas cyanide is not a very strong base. So what happens first is a proton transfer step. So cyanide is apparently not a good enough nucleophile by itself, so we add HCl. That transfers a proton to the oxygen, which makes it a better electrophile. Cyanide can now come along and attack, which gives us our cyanohydrin. So we have a cyanide and an OH. This is called a cyanohydrin. These are stable. We can isolate them, and they are pretty useful intermediates, as we're going to see on the next slide. So what can you do with cyanohydrins? Well, in future units, what we're going to do is talk about reactions of nitriles. For now, you should know that you can use lithium aluminum hydride to reduce a nitrile. So carbon-nitrogen triple bond can be reduced. So we put 2 hydrogens on the carbon, 2 hydrogens on the nitrogen to get a primary amine. So this is a nice way to make amino alcohols. If you start with a cyanohydrin, you can make an amino alcohol. Or you can hydrolyze a nitrile to get a carboxylic acid. So this gives you what we call an alpha hydroxy acid. So this carbon becomes the carbon of our carboxylic acid in the presence of dilute acid and heat. Okay, the next reaction we're going to talk about, which is a really cool reaction, is the Wittig reaction. The Wittig reaction makes alkenes, or makes carbon-carbon double bonds. So we have a carbon-carbon double bond starting with a carbon-oxygen double bond. Remember, in ozonolysis, we take a carbon-carbon double bond and we turn it into a carbon-oxygen double bond. So you can think about the Wittig reaction, it's pronounced Wittig, like a V. You can think of the Wittig reaction as the opposite of ozonolysis. We're taking a carbon-oxygen double bond and turning it in to a carbon-carbon double bond. What we use in the Wittig reaction is a reagent called an Ylide, Y-L-I-D-E, Ylide. And this is a reagent that possesses a phosphorus-carbon bond that has an internal dipole or charge, like the phosphorus is positively charged and the carbon is negatively charged. We can draw a resonance structure of this species where the carbon and phosphorus are double bonded to one another. But this resonance structure is the most useful because it shows us that the carbon is a nucleophile. We have a nucleophilic source of carbon in our Ylide, which is going to help us understand the mechanism to get to our carbon-carbon double bond. So the resonance structure that I was talking about is this one. So one way you can think about the Wittig reaction is you're exchanging a carbon-oxygen double bond in a reagent and a carbon-phosphorus double bond for a carbon-carbon double bond, and the other byproduct of the reaction is triphenylphosphine oxide. So we replace a carbon-oxygen double bond and a carbon-phosphorus double bond for a phosphorus-oxygen double bond and a carbon-carbon double bond in the products. Okay, so what's the mechanism of the Wittig reaction? For the sake of neatness and time, I'm just going to show the reaction of acetone with a simple Wittig reagent that we had on the previous slide. So let's say we do the methyl Wittig reagent. I'm going to abbreviate the phenols with a pH. We have a formal plus charge on our phosphorus, and we have 2 hydrogens and a negative charge on carbon. We said carbon is nucleophilic, so that's going to it's a very strong nucleophile, so it can attack without any encouragement from an acid catalyst, right? And we get an O minus here. This carbon is bonded to this carbon, right? And that carbon is bonded to a phosphorus that has 3 phenols on it, and that's positively charged, right? So we have a negatively charged oxygen very, very close to a positively charged phosphorus atom. And so what can happen now is the negatively charged oxygen attacks the positively charged phosphorus, and what we get is a 4-membered ring intermediate, which looks like this. Okay, and then what can happen now is this ring is very, very strained. So what it wants to do is relieve that strain, and one way it can relieve that strain is by these 2 electrons become our phosphorus-oxygen double bond, and these 2 electrons become our carbon-carbon double bond. So very simply, at the end of the reaction, we have a carbon-carbon double bond here, and a carbon-phosphorus double bond here, and those are our products. So this carbon has 2 hydrogens on it, and those are our 2 products of our Wittig reaction. Okay. Where does this Wittig reagent come from? It's actually really easy to understand how to make a Wittig reagent. You take triphenylphosphine and you react it with an alkyl halide, like in this case methyl iodide, followed by butyllithium. So what's the butyllithium there for? Well, the mechanism here is pretty straightforward. We have triphenylphosphine, and just like an amine, right, phosphorus can make 3 bonds and have 1 lone pair. So if we treat that with an electrophile, we can have an SN2 reaction where the phosphorus attacks the carbon, we kick off the iodine. So now we get what's called a Wittig salt. We have a positive charged phosphorus, and we have the iodide counterion. And what we want is a negatively charged carbon, right? So what we do is we add a very, very strong base, butyllithium. And what butyllithium will do is remove one of these hydrogens to give a negatively charged carbon, and that gets us to our Wittig reagent. So step 1 is an SN2 reaction. Step 2 is a proton transfer to form our Wittig reagent. Okay, the last reaction that we're going to talk about in this video is called the Baeyer-Villiger oxidation. This is a really weird reaction. You start with a ketone or an aldehyde, and what you do is you stick an oxygen in between the carbon of our carbon-oxygen double bond and one of the groups that's bonded to our ketone and aldehyde to get an ester functional group. The way that we do this is with a per acid, and the two most common per acids that you'll see are per acetic acid, right, or MCPBA is commonly used, meta-chloroperbenzoic acid. So either one of these reagents can be used to carry out the Baeyer-Villiger oxidation, which what we're doing is we're sticking an oxygen atom between a carbon and an adjacent R group. This is really useful for what's called ring expansions, right? So let's say you have a 5-membered ring ketone. This is cyclopentanone. You can turn that into a 6-membered ring lactone, which is a cyclic ester, by Baeyer-Villiger oxidation, which sticks an oxygen in between these two carbons. So what's really important in the Baeyer-Villiger oxidation is to count your carbons. Let's say this, we said this has 5 carbons, right? The product still has 1, 2, 3, 4, 5 carbons, but we stuck an oxygen between carbon 1 and 5, so now we have a 6-membered ring. So be careful when you're drawing the products of your Baeyer-Villiger oxidations. What's the mechanism of this crazy reaction? Again, to keep it somewhat simple, let's say we have per acetic acid, which is an acid, so we're under acidic conditions. So most likely the first step is a proton transfer. We transfer a proton from our acid to our ketone, right? That becomes protonated, so now it's subject to nucleophilic attack. And we have this peracetate ion, which has a negatively charged oxygen, which can nucleophilically attack, which gets us to our tetrahedral intermediate. We have an O and an O. And there's a lot of ways you can draw this mechanism, but what I think is the easiest is to remember that these oxygen-oxygen bonds are extremely weak, right? And so what can happen is that a base, like another molecule of peracetate, can come along. So let's draw that as the base. That accepts a proton. These two electrons form a carbon-oxygen double bond. The trick for the Baeyer-Villiger oxidation is now these two electrons in the bond migrate up to the oxygen, which then breaks this really weak bond to form acetate. So the products here, let's think about all the products. So we have this CH3. Now this carbon is double bonded to oxygen, right? We lost the proton. This carbon is bonded to an oxygen, which is now bonded to a CH3. So in effect what we did was we stuck an oxygen atom in between this carbon of our carbon-oxygen bond and the methyl group right here. Okay, what's really important to remember about the Baeyer-Villiger reaction is if you don't have a symmetrical ketone, let's say you have an isopropyl group here and a methyl group here, that the more substituted group is going to migrate faster, so the oxygen is always going to get stuck in between the carbon of our carbon-oxygen double bond and the more substituted carbon. So the migratory aptitude is hydrogen is the fastest, then tertiary carbon, secondary carbon, primary carbon, and methyl. Okay, so that sums it up for all reactions of ketones and aldehydes. We can group these into several groups. Oxygen-containing nucleophiles that form acetals, sulfur-containing nucleophiles that form thioacetals, nitrogen-containing nucleophiles form imines and enamines, hydrogen nucleophiles like lithium aluminum hydride and sodium borohydride, carbon nucleophiles like Grignard reagents, cyanide, and Wittig reagents, and don't forget the Baeyer-Villiger oxidation. To understand the mechanism, in each case, ask yourself, is this acidic or basic conditions? To summarize everything, metal hydrides reduce ketones and aldehydes. Carbon nucleophiles can we are already familiar with, Grignard reagents. Cyanide can make cyanohydrins. Wittig reactions give us carbon-carbon double bonds, and the Baeyer-Villiger reactions gives us esters or lactones.